Welcome students for the PowerPoint presentation of physics for class 12. In this session, we will study about electromotive force, grouping of cells, Kirchhoff's law rules, combination of resistances, electrical energy and power, Wheatstone Bridge, meter bridge, and finally we will conclude with discussions on potentiometer. Welcome once again. Please note down all the important points discussed here as the same will be helpful for you in your examinations. Electromotive force. It is also called EMF. If dW is the work done to move a positive charge dq from negative to positive terminal of a battery, then the EMF, that is the work per unit charge of device, is given by the equation E equals dW by dq, where E is the EMF, dW is the work done and dq is the charge. An EMF device does work on charges to maintain a potential difference between its output terminals. The volt is the SI unit of EMF as well as the potential difference PD. Please see the figure on the right hand side. Here a battery or a cell is shown with light blue colors filled with electrolyte. P is a positive terminal and N is a negative terminal. Here I is the current flowing through the circuit. R is connected between points C and D. A current I starts from positive terminal of the battery, flows through this point and goes through this, and R is the resistance connected across positive and negative terminal, and it comes back here. E is the electrolyte, and the symbol of the cell is given by a larger plate and a smaller plate. One larger plate is normally recognized as positive and smaller one is represented by minus sign. So R is the connected resistance across the battery. So we will repeat, an EMF device, that is a battery, does work on charges to maintain a potential difference between its output terminals. Output terminals are C and D. The volt is the SI unit of EMF as well as the potential difference PD. Let us differentiate between EMF and potential difference. EMF is the potential difference between two terminals of a cell when it is not supplying any current. That is, if there is an open circuit and this terminal C and D are not connected with any resistance and it is left open, then the potential difference available between P and N or between C and D after removing the resistance without R, resistance R is EMF. The potential difference is the voltage across two terminals of a cell when it is supplying current to an external circuit or terminal voltage. That means when a resistance R is connected across the cell between terminals C and D as shown in the figure, a current flows through the resistance R and this voltage is called, between these two terminals, is called potential difference. So the main difference is EMF is when there is an open circuit and it is not supplying any voltage to the resistor, and potential difference when a load or a resistance is connected across two terminals, then it is called potential difference. Internal resistance of a battery. In case of a cell, the opposition of the electrolyte to the flow of current through it is called internal resistance. That means when a load is connected, the current is supplied to the load, that is resistance. So when initially it starts, the battery or the cell or the electrolyte opposes the flow of current. This opposition is called the internal resistance of the battery. Internal resistance Ri equals 0 for an ideal EMF device. That means the Ri, that is the internal resistance of the battery, equals 0 for an ideal case, but in practical cases this is not 0. The potential difference between terminal is equal to EMF when Ri equals 0. A real EMF device has internal resistance. An electrolyte cell. Having studied about these circuit configurations, let us know what is this cell. An electrolytic cell is a device which supplies a steady current in an electric circuit by converting chemical energy. There is electrolyte here, and this electrolyte converts chemical energy into electrical energy. It has two electrodes, positive, it has two electrodes for a positive electrode and a negative electrode. Dipped in electrolyte, both these electrodes are dipped in electrolytes as shown in the figure. So in this lecture, till now we have studied about electromotive force. Electromotive force is equal to work done per charge, that is E is equal to dW by dQ. So there is a difference between EMF. We have learnt about the difference between EMF. EMF is when no load is connected, it is an open circuit and no current flows. So it is EMF. Potential difference is 1 when we connect a load and current is supplied to the external load R. So internal resistance is the resistance offered by the electrolyte and internal characteristics of the battery which opposes the delivery of the load, and it is represented by Ri. Sometimes here we have shown it as Ri, and most of the time we represent it as small r. Electrolyte cell is a device which supplies, it is a source of current. It is source of current which supplies a steady current in the electrical circuit. The upper part of this is called electrical circuit. By converting, the cell converts chemical energy into electrical energy. It has two electrodes P and N dipped inside an electrolyte as shown in the figure. Grouping of cells. Please see the figure on the right hand side. Here a number of cells or batteries are connected together in the sense one after the other. Here the cell E1 is connected to cell E2, and which is in turn connected to cell E3, etc., one after the another. That means a positive cell, a positive electrode P is connected to the load, one side of the load, and the negative side of the battery or the cell minus is connected to the positive of the cell. So negative of one cell is connected to the positive of the other cell. So, similarly, negative of the second cell is connected to positive of the third cell, etc. Like this we can connect a number of batteries one after the another. Such a connection wherein positive is connected to the load and the negative is connected to another cell, and similarly negative of one connected to positive of another is called a series, cells in series. Here the equivalent voltage or the potential difference will be EQ. Equivalent will be equal to E1 plus E2 plus etc to the to up to n. Here we have taken only two cells, so E equivalent will be equal to E1 plus E2. And the internal resistance of the batteries also will be given by R1 plus R2, where REQ is the equivalent resistance of the combination, that is equal to internal resistance of the battery 1 or cell 1, and R2 is the internal resistance of the cell 2. When we connect, there is yet another type of connection of cells, that is called parallel. Here you please see, this is the positive, the longer plate is a positive of the cell 1 E1, and longer side of this is positive cell of E2, and this is a positive of the E3. So all the positives are connected together, and similarly the negative, that smaller side, is connected together. All the three, E1 is here, E2 is here, and E3 is here. All the three are connected together. This type of connection, where cell positive plates of the cell or the positive electrodes are connected together and negative are connected together on the other side, and they are in turn connected to the load as shown in the diagram, are called cells in parallel. That is, the current flowing from here, from the batteries, combines and flows to the resistor. Here also current flows through each of the batteries in the previous case, but connection is different type. Please note the difference between a series connection and a parallel connection. This is cells in series and this is in cells in parallel. Here the reciprocals get added. Therefore, the resistance of cell is 1 over Req, that is equal to reciprocal of internal resistance, equivalent will be parallel connection, that is 1 by R1, where R1 is the internal resistance of cell 1 and R2 is the internal resistance of cell 2, etc. It goes up to 1 over Rn if n number of cells are connected in parallel. Sign convention. When we are studying about the batteries, it is important to know the sign convention for solving the circuit problems. Please see the figure here at the bottom. Here there are two terminals A and B, and a resistance R is connected through between these two terminals, and you see current is entering into the resistance. So you say the current is entering into the resistance. When current is entering into the resistance, the potential drop across resistance R is given by I into R, and in this case we have to take the sign as minus IR. The potential drop across resistance R is minus I into R. Let us take in another case where current is flowing in the opposite direction. Therefore, if the current is flowing in the opposite direction, then it is plus R. The potential difference will be plus R. Please see the figure, fourth figure here. Here positive plate is there and potential is minus E. In this case, the positive, if the current is flowing from here, entering here, and it is in the opposite direction, it is plus E. The change in potential in transferring a resistance R in the direction of current is minus R, and opposite to that is plus IR. That is, if the external current is flowing like this, and in the circuit calculation we are taking in this direction, it is plus IR. Whereas in this case the current is flowing like this, and our circuit mesh current is also in this direction, so it is positive. It is negative and positive here. The batteries are also, if current is flowing from positive to negative here in the battery itself, it is minus E, and if we move from right to left as shown in the figure, that is negative plate to the positive plate, it is plus I plus E. The change in potential, here it is the change in potential transferring an EMF source, E or EMF source from negative to positive is taken as plus E. From negative to positive it is taken as plus E, and in the opposite direction, that is positive to negative, if then it is minus E. Open circuit. When no current is drawn from the cell, it is an open circuit. A closed circuit is one wherein the cell supplies the constant current to the circuit. In all these cases, I is equal to E divided by R plus R. I is equal to E divided by small r plus capital R. Small r is the internal resistance and capital R is the load resistance. This is the external resistance connected to the circuit. So this capital R is the load resistance or the connected resistance. Small r is the internal resistance of the battery, which is not shown in the circuit, but it is written along with the EMF, that is E into R. This R indicates the internal resistance of the battery. So in the case for calculating potential difference, we take V is equal to I into this R plus small r. V is equal to small I into R plus R. Potential drop inside the battery due to internal resistance is given by I into small r. That is the power loss due to internal resistance of the battery. Therefore, internal resistance can be expressed as R is equal to, by simplifying and calculating from these two equations, that is equation 3.11a and 3.11b, we find internal resistance is equal to, internal resistance R is equal to E by V minus 1 into R. This is equation 3.11d. So, while grouping of cells, the cells connected in series, the EMF acts algebraically and the resistance, internal resistance also acts. When the cells are connected in parallel, their reciprocals act, that is 1 over R equivalent will be 1 by R1 plus 1 by R2 plus etc. etc. The current through the circuit is given by I is equal to E by R plus R, small r internal resistance plus load resistance. Potential difference V is given by V is equal to I into R plus R. Potential drop across the internal resistance battery is given by I into R, the current drawn into the internal resistance. Internal resistance is given by R is equal to, open the bracket, E by V minus 1 in close the bracket into capital R. These are the equations. We have equation 3.11a, 3.11b, 3.11c and 3.11d. Please remember all these four equations, as these will be helpful for you in solving numerical problems. Now let us study important laws. These are called Kirchhoff's laws. Some people call it as Kirchhoff and some people call it Kirchhoff's. In Western countries they call it Kirchhoff's laws. These are also called junction or loop rules. Kirchhoff's first law or junction rule. The sum of currents entering a junction must be equal to sum of the currents leaving. That means if I1 and I3 are the current entering into a junction, and I2 and I4 are the currents leaving the junction. Then the sum of currents entering the junction equal to sum of currents leaving the junction. Please see the figure at the bottom. Here there are two. Please note it is a junction here. This is a current junction where I1 is entering the junction, I3 is also entering the junction. The arrow marks are shown into the junction. So these are I1 and I3 are two currents entering the junction. Therefore they are added, I1 plus I3. Here the I2 is leaving the junction, I4 is also leaving the junction. Therefore their sum I2 plus I4. So the sum of I1 plus I3 equals I2 plus I4. Kirchhoff law can also be stated in another way. The algebraic sum of all currents meeting at a junction in a closed circuit is 0. Therefore, if you take I1, I2 and I4 towards left, so there will be the algebraic sum of all currents meeting at a junction in a closed circuit is 0. Therefore, sigma I is equal to 0. This law is also known as Kirchhoff's current law. This law follows law of conservation of charge. The number of charges arriving at junction should be equal to the number of charges leaving the junction at the same time. So conservation charge is related to charge, which says the number of arriving charges will be equal to charges leaving the junction. Sign convention of a junction. Incoming currents are positive, outgoing currents are negative. So I1 and I3 are positive and outgoing currents I2 and I4 are negative. Kirchhoff's second law or loop rule. The previous law was related to currents, sum of currents. This second law is related to the potential drops. It states the algebraic sum of all potential drops and EMFs in any closed circuit is 0. That means sigma V, that is potential drop, equals to 0. This law is also known as Kirchhoff's voltage law. Please see the diagram at the bottom. Here E1 and E2 are the two cells supplying the current to the circuit, and there the potential drops are open circuit voltages are E1 and E2. Loads and resistances are connected as shown in the figure. So the current I1 leaves the cell E1 and it gets divided here like this. Similarly, E2 is connected at the bottom as shown, and it leaves I2 current leaves here, and these two currents I1 and I2 combine and flow into the resistance R2. And again, after passing through R2, this current gets divided as I1 towards C and B and I2 towards C and D. So I2 flows from right to left and I1 flows from bottom to top. This is a circuit diagram for a given figure. This law represents law of conservation of energy. If there are n meshes in the circuit, there will be n minus 1 number of independent equations. Here, let us repeat Kirchhoff's second law. The algebraic sum of potential drops and EMF in any closed circuit is 0. That means E1 is the supply, E1 equals the drop across R2, and the current through R2 is I1 plus I2 into R2, and again in this loop I1 into R1 equals 0. E1 minus of I1 I2 into R2 minus I1 R1 equals 0. Similarly, we can write equations for the other network. So let us see loop A, B, C, A. This is the loop A, B, C, and going back it is A. This is the loop A, B, C, A. Here, even in this mesh or network, there is a supply E1. This E1 is equal to I1 into R1. See, I1 into R1 and plus I2 into I1 plus I2. This current flowing through R2 is I1 plus I2 into R2. Therefore, because we are going for calculation purpose, we are going clockwise. Clockwise we are going. So E1 is equal to I1 R1 plus current through R2 is I1 I2 into R2. Then consider the second loop in the same network, same mesh A, C, D, A. Here also for calculation purpose we have taken a clockwise direction. So algebraic sum. Here E2 is the voltage. So E2 equals, if we go like this, E2 equals I1 plus I2 into R2, current flowing through R2 in plus I2, here current is I2 into R3. So if you bring everything on the left side, then the right side becomes 0. Therefore, sigma V will be equal to 0. So this is the statement of Kirchhoff's second law. Algebraic sum of potential drops. This potential I1, I2 into R2 plus I2, R2 are called potential drops. They are consuming power. E2 is the supplying power. Therefore, sum of E2, that is sum of potential drops plus EMF in a closed circuit. This is a closed circuit. A, C, D, A is a closed circuit. Similarly, A, B, C, A is another closed loop or closed circuit. So here the algebraic sum of all potential drops and EMF is 0. Combination of resistances. Resistance in series have the same current. Please see the figure on the right hand side. Here three resistances R1, R2 and R3 are connected to a cell or a battery supplying a potential drop of V volts. So a current I starts from the battery and flows through resistance R1, then the same current goes through R2 and same current flows through R3. That means resistances in series have the same current. Please note, resistance in series have the same current. Here this potential V gets divided into three parts, R1 across R2 and R3. So current is same. The potential drop or the voltage is I1 into I is same, I into R1. Similarly, the potential V2 across R2 will be I into R2. And the third resistance will be V3 will equals I into R3. So this V gets divided into V1 plus V2 plus V3 in the ratio I into R1 plus I into R2 plus I into R3. Combining V1 plus V2 plus V3, we get V is equal to I into R1 plus R2 plus R3. That means the equivalent resistance will be Req will be equal to R1 plus R2 plus R3 plus etc. This can also be written as R1 plus R2 plus R3 can also be written as sigma J is equal to 1 to N Rj. Let this be equation 3.13. This equation will also be helpful for us in solving numerical problems. Let us take up the second case where the resistances R1, R2 and R3 are connected in parallel. When we say in parallel, that means the current I gets divided into I1 through R1, I2 through R2, I3 through R3. In the previous case, please note the difference. Previous case, same I was passing through R1, R2 and R3. In parallel, it is getting divided. Resistances in parallel have the same potential difference. You see here, this terminal 1 and this is another terminal have the same potential V. So, the resistances in parallel have the same potential difference V. Therefore, I1 will be equal to the current through resistance R1 will be equal to V divided by R1, and I2 will be equal to V same voltage divided by R2. The third one, I3 will also be equal to V divided by R3. So the current is getting divided, whereas the potential difference remains same. I1 equals V by R1, I2 equals V by R2, and I3 equals V by R3. Now we have to, previously we added V1 plus V2 plus V3, but here in parallel, in the case of parallel resistances, we have to add currents I1 plus I2 plus I3. Therefore, adding V by R, if R is the total equivalent resistance of the combination of three resistances in parallel, that is given by V into 1 by R1 plus 1 by R2 plus 1 by R3. Because I1 is equal to 1 by R1, I2 is equal to 1 by R2, and I3 is equal to 1 by R3. Please see this equation. So reciprocals are getting added here. Therefore, cancelling this V, left V and right V, on the right hand side V, we get 1 by R, that is 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by R1. That can also be written as sigma J equals 1 to N 1 over Rj. This is the resistance, equivalent resistance in parallel connection. Please remember both the equations, equation 13.A as well as equation 13.B. It is the repetition of the previous equations. So both the equations are also important for solving numerical problems. Electrical energy and power. When a potential difference is applied across a conductor of a resistance R, free electrons in a conductor move from a lower potential to a higher potential and strike the atoms of a conductor inelastically. That means when an external potential difference is applied to a resistor R, the electrons inside that conductor will move and gain the energy and start moving. In these collisions, and they collide with one another. The electrons collide with the atoms. In these collisions, energy is released in the form of heat or light, as the case may be. So electrons gain energy, but they don't move out of the conductor, but the energy is dissipated as heat or emitted as light. Thus, the energy dissipated as heat in the conductor during the time interval dt is the work done. Delta W is equal to IV into delta T, where I is the current and V is the voltage, and the energy dissipated for time T is delta T. The energy dissipated per unit time is the power dissipated. That means if we divide the work done per minute or per second or per hour, dW by dt IV is equal to power. Therefore, we have P is equal to V into I, voltage into current, where V is the voltage and I is the current. That is also equal to I square R, because V is equal to V into I. Therefore, that is written as V I square into R. Similarly, we can write it in terms of V only. Therefore, V square I into R is V. I into R is V, and R is also equal to I by R. The I into R. So it can be written as V square by R. So let us repeat this equation. Power is equal to voltage into current. That can be written as, substituting for V as IR, we can write VI is equal to I square into R. That can also be written as, because I is equal to V by R, therefore this becomes V square by R. If you put the values of internal resistance, this equation can be written as P is equal to E by, that is the EMF, divided by R plus R whole square. This is the current. E by R plus R is I whole square into R. This equation is 3.14 E. The SI unit of power is watt. So the product of VI is called power and its unit is watt. Most of the time we are using kilowatt hours. In our house, the energy consumed is measured as kilowatt hours. That is the kilowatts we use per hour. Hence, kilowatt hour is the energy consumed by a device of 1 kilowatt in 1 hour. Suppose we connect a load of 1 kilowatt and use it for 1 hour, then kilowatt hour is 1 kilowatt hour. So, having known about the power and electrical energy, let us find a condition for maximum power transfer. You know very well that there are losses when the current flows, but these losses can be reduced under certain conditions. That condition is, if the value of internal resistance R equals the load resistance R, then maximum power is delivered to the load. So, in such a case, when R is equal to, small r is equal to capital R, then P, power maximum, is equal to E square divided by 4R. This is the equation for maximum power. For example, we will say when we connect electric bulbs in combination that we normally use in our houses. If an electric bulb of power P and rated voltage V is operated at a voltage V dash, the power consumed by bulb is P dash is equal to V dash divided by V into P. If you see an electric bulb, the rated voltage will be written as 230 or 220 volts, and a 40 watt bulb, that P is 40 watt bulb, 30 watt bulb, 50 watt, 100 watt bulbs. So this is the rating on the bulb. If an electric bulb of power P and rated voltage V is operated at a voltage V dash, the power consumed by bulb is P dash is equal to V dash by V into P. Bulbs in parallel. P is equal to P1 plus P2. If we connect two bulbs in parallel, the power consumed will be equal to P1 plus P2. If we connect bulbs in series, one after the other, their reciprocals add. 1 over P equals 1 over P1 plus 1 over P2. In this section, we will study about the Wheatstone Bridge. Wheatstone Bridge is a network of 4 resistors. This is R1, this is R2, R3 and R4. Resistance R1 is connected between terminals A and D, and R2 is connected between A and B. This is R2. Similarly, the resistor R3 is connected between terminal D and C, and R4 is connected between terminal B and C. This is the standard form of Wheatstone Bridge. A galvanometer G is connected between terminal B and D. Wheatstone Bridge is used for knowing the for measuring the value of unknown resistor. In this circuit, R4 is the unknown resistance. So Wheatstone Bridge is a network of 4 resistors R1, R2, R3 and R4. This is R1, R2, R3 and R4. R4 is the unknown resistance. Galvanometer G is a galvanometer which indicates the deflection or flow of current. R3 is adjusted, the resistance, standard resistance or a rheostat, a variable resistance, standard whose value is known, is adjusted to get zero current through galvanometer. This resistance is adjusted so that no current flows between the terminals B and D. Here it is 0, which is indicated by the deflection of the galvanometer. Therefore, Ig equals 0. That is the balance condition. After adjusting this and no current flows, it is called the balance condition. Therefore, under such a condition, the current flowing from the battery source or a voltage source which goes through these terminals gets divided. This I2 goes towards AB and I1 goes towards AD. So the ratio, the current will be I2, this current I1 flows through R1, and since no current flows through galvanometer, the entire current goes through R3. Therefore, it goes like this. I3 goes like this, and similarly I2 gets divided. Under balance condition, I2 will be equal to I4. See, the same current I2 will be equal to I4 because no current flows. Similarly here, I1 will be equal to I3 because no current flows through the galvanometer. This is called the balance condition of the bridge. As I said earlier, a battery is connected, a battery source is connected between the terminals A and C. Consider the loop A, B, D and A. Here I2 into R2 minus I1, because we are going in the opposite direction of the current minus I1 R1 equals 0. Therefore, I2 R2 will be equal to I1 R1. Therefore, here you take it on the right side and divide I1 by I2 is equal to R2 by R1. Consider another loop BCDB. Here also the current I4 is going, I4 into R4, we are going in the direction of opposite flow of current, minus I3 into R3 equals 0. And simplifying, we get I3 by I4 is equal to R4 by R3. Under balance condition, Ig equals 0. Therefore, R2 by R1 equals R4 by R3. From this equation that is R2 by R1 is equal to R4 by R3, we can find the value of R4, which is given by R4 is equal to R3 into R2 by R1. So, this is the equation of a Wheatstone bridge under balance condition. R4 is equal to R3 into R2 by R1. In this way, we can calculate the value of unknown resistance from using a Wheatstone bridge. R1 and R2 are known resistances. Please note R1 and R2 are known resistances. R3 is a variable resistance such that we can bring the balance condition of bridge, that is Ig equal to 0. R3 is adjusted to make Ig equals 0. Ig is the current through galvanometer. Ig is not shown because it is 0 here. Now let us study about the meter bridge. The diagram or the figure of a meter bridge is shown on the left hand side. Here E is the supply and A and B are the two terminals between which we are connecting a meter wire. Meter bridge works on the principle of Wheatstone bridge. The meter bridge consists of 1 meter length of wire clamped between terminals A and B as shown in the figure. Here are the two terminals A and B. The length of wire is 1 meter because it is a meter bridge. The length of meter here between A and B is 1 meter and the length of wire is 1 meter. The end points are connected to a cell E. Between A and B, we have connected a cell E with a key K. The standard resistance R, this is the resistance box or a standard resistance R, and unknown resistance X are connected at the open terminals. These are the open terminals. This is one open terminal and this is also open terminal. Here we connected a standard resistance and here we connected unknown resistance. The galvanometer is connected between the terminal of the wire and a jockey to the wire. The galvanometer G is connected as shown in the figure. J is called the jockey J. So X is the unknown resistance whose value we are required to measure. The galvanometer current is made 0 by adjusting the jockey. By adjusting and moving the jockey along the wire, potentiometer wire or a meter bridge wire, we bring J into 0. The galvanometer current is made 0 by adjusting the jockey position on the meter wire for values of known and unknown resistances. Hence, here we have connected a known resistance and an unknown resistance and we are adjusting this in such a way that there is no current through galvanometer. Resistance of the wire is proportional to the length of wire. In such a way that the ratio R is a known resistance divided by unknown resistance is equal to RAJ. The resistance between this point, suppose the jockey point is J here, AJ, RAJ, resistance of RAJ divided by RJB. That is equal to L. If this is the L centimeter and this is 100 minus L, because 100 is 1 meter we have taken. Okay, 100 minus L minus 100. Therefore, from this equation we can find the value of X. This is the use of meter bridge. Therefore, X goes to numerator. X is equal to R into cross multiplying L minus 100 divided by L. In this way, we can find the value of unknown resistance. This equation is repeated once again for you to remember. Next, we will study about a potentiometer. Potentiometer is a device to compare electromotive forces, EMFs, and to determine the internal resistance of the cell. Please see the figure on the right hand side. Here, the diagram of a potentiometer is shown. The upper part comprises of a battery or a source small e with internal resistance R and a variable resistance RH rheostat through a key K. This circuit is called the primary circuit, and in between A and B a long wire is connected. Potentiometer consists of a long resistive wire AB. AB is a long resistive wire of the order of 6 meters to 10 meters. In the previous meter bit, we had used standard 1 meter, but in potentiometer, we are using a long wire of length L varying between 6 meters to 10 meters. It is made up of manganese or constant 10 and a battery of known voltage. This is a known voltage, a battery of known voltage E and whose EMF is to be measured, and resistance R, internal resistance. One terminal of the cell, one cell whose EMF is to measure, is connected at one end to the main circuit. This is the main circuit, and this is the galvanometer, and it is a jockey at a point resistive wire through a galvanometer. Here I will describe the figure once again. J is the jockey, K is the key, R is the resistance of the potentiometer wire. This is the R, value of R is the resistance of the potentiometer. RH is the variable resistance which controls the flow of current through wire AB. Principle of potentiometer. We know V is equal to I into R. The potential difference across AB is given by I into R. Retaining I, we can substitute R by its specific resistance into length of wire divided by the area. That is, we know R is equal to rho L by A, where rho is the specific resistance, L is the length of the wire, and A is the cross section of the wire. So cross section, if we keep constant, the rho of manganese R constant 10 is constant, and its temperature coefficient of resistance is also low. Hence, we use that material for potentiometer, and we calculate using this equation. V is equal to I into rho L by A. Therefore, V in this equation, if we keep current as a constant, V is proportional to the length of wire. The potential difference or fall in potential per unit length of wire is called potential gradient. This wire has got a potential gradient, that means its voltage or potential falls as we move along the wire of length 6 meter to 10 meter. Therefore, potential gradient X is given by V divided by M, where M is the meter, and V is equal to I into R, that is equal to I, value of I here is E divided by R plus RH plus R. E is the battery voltage, R and internal resistance plus R. The potential difference is proportional to its length when a constant current flows through it. If we keep the current constant, the potential difference V is directly proportional to L, length of the bridge, L, that is the point between A and J. The potentiometer has the advantage that it draws no current under balance condition from voltage source being measured. That means if you want to know the voltage of the battery or conduct measurements on E, it draws no current from this. As such, it is unaffected by the internal resistance of the source. If V is constant, if the potential difference is constant, then it is given by The equation is given by x1 by x2 under two different cases. L1 by L2 equals L1 by L2. About these equations we will study further in the next slide, where we take up the cases of comparing EMF as well as measuring the internal resistance. So potentiometer consists of a long resistive wire AB made up of manganese or constantine and a battery of known voltage E and resistance R. One terminal of another cell, this is called primary. Okay, one terminal of another cell whose EMF is to be measured. We are supposed to measure the EMF of this cell is connected at one end of the main circuit. This is main or primary circuit. This is secondary circuit. This E is connected to A and G is connected through a jockey to the potentiometer wire. Hence, the potential gradient x is equal to V by M, or it is equal to E divided by R plus RH plus R into R. Working of potentiometer. So please see the circuit on the right hand side. This is meant for comparing two EMFs of cells of two EMF. Here there are two cells E1 and E2. We have to compare E1 and E2 using a potentiometer. Here is a key K dash is a two-way switch. Here is a central point. It can connect either to terminal 1 or terminal 2. Hence it is called two-way. One way is connecting terminal 1 and second way is to connect terminal 2, and the other end is a galvanometer. And here also we have a jockey which moves and connects the potentiometer wire to the sources of supply. Here we compare EMF of two cells E1 and E2. One of the cell can be unknown. For example, let us see that take for example E1 is not known. E2 is if we can connect a E2 as a standard cell whose voltages and internal characteristics are known and whose voltage is very stable and is not vary. We can connect and we can balance and measure the distances AJ, say AJ1 and AJ2. AJ1 when we connect cell E1 and AJ2 when we connect cell E2 to the circuit, primary circuit, and balancing lengths are L1 in the first case and L2 in the second case. Then the ratio E1 by E2 equals L1 by L2. Please see here the equation E1, where E1 is the EM of the first cell and E2 is the EM of the second cell, and the balancing is equal to L1 by L2, where L1 is the balancing length of first case when it is E1 is connected to the circuit through terminal 1, and L2 is the balancing length of the circuit or the potentiometer when this common terminal is connected to the point B, point 2, and L1 and L1 are measured. Hence E1 by E2 equals L1 by L2. Hence we can compare the EMFs of the two cells. Then the next case is measurement of internal resistance. The circuit is slightly different. Here we don't use two cells in the secondary circuit. We use only one circuit for measuring internal resistance. Please note, for measuring internal resistance, the primary circuit is same, the upper circuit is same. Only in the secondary circuit, we remove one cell and connect only one through a key K dash and a resistance R dash as shown. The details of these connections we will discuss now. So J is J, G and all other things are same. Only this connection we have removed E2 and connected a resistance R dash. The circuit for measuring internal resistance of a cell is shown in the figure. The cell E whose internal resistance R is to be determined is connected across a box R dash. This is a box, resistance box R dash through a key K dash as shown in the figure. When the K dash initially K is open and we balance the length of the wire through jockey, we get E is equal to X into L1, that is X is the potential gradient is equal to L1. We proportional to first we get internal resistance is added into the circuit. Therefore, the current is a function of I into R plus R. I into R plus R. Therefore, E in the first case without this resistance box is I into R plus R, internal resistance. Then again we connect K2 is closed. Now we close the E2. K2. The cell sends a current I through the resistance R dash. This current sends a current through this R dash, and the second balancing length L2 is obtained. That is first without R dash, second with R dash. So in the second case, V is equal to X into I2 or X is equal to X into L2. L2 is the balancing length. Therefore, in this case, V will be equal to I into R dash. Dividing the previous equation, E equals XL1 divided by XL2, we get E by V is equal to I into R plus R, R plus R and then I R dash. That is equal to L1 divided by L2. Therefore, we can calculate R internal resistance as equal to R dash into L1 by L2 minus 1, or it can also be written as R is equal to L1 minus L2 divided by L2 into R dash. So, repeating, there are the uses of potentiometer, main uses. One is comparing the EMF of two cells where we connect two cells, one standard and one known cell in the secondary circuit of the potentiometer, and we calculate the unknown EMF or compare with E1 standard EMF using the equation E1 by E2 equals L1 by L2 by balancing the lengths L1 and L2. In the case of measuring an internal resistance of a cell, we use this circuit, the lower circuit, where in the secondary circuit we connect only one battery, unknown battery, whose internal resistance is to be measured, and a resistance box. Initially we disconnect R dash and measure the internal resistance. We measure the current which is proportional to the L1. That is, we measure the length for balancing without R dash. In the second case, we add R dash and we measure the length in such a way to balance it. Therefore, the internal resistance R is given by L1 minus L2 divided by L2 into R dash. With this, we conclude the working of a potential. Now, we have studied about the EMF Kirchhoff law and the electrical measurements, and we have come to the end. In the next chapter we will summarize the current electricity once again, and we will take up work examples. Please study whatever we have learned in this lecture and come prepared for the next class. Thank you very much.